welcome to this very special event. I mean, we called it the Game Theory, the Math 308 Special, the April 16 Special. At the suggestion of students, we asked Professors Nash and Kuhn whether they would be willing to have a presentation to the class, and we are very, very grateful that they accepted. And so this is it. As you know, as students know, we have collected questions, and after we start with a little presentation by Harold Kuhn and John Nash, and then after their presentations, there will be a question-answer session. Sam and I will have microphones with which we walk around so that people who have a question can have a microphone to ask the question so that everybody can hear it. And we'll take it until time runs out, or until Professors Nash and Kuhn would like to stop. So that's the rules of the game. I mean, it's a game theory class, so we have to have rules. So I will no longer waste any more time, and I'd like you to join me in welcoming our guests.
I thought I would start by giving you a little bit of history about how game theory came to Fine Hall. Ingrid sent me last night the list of the questions that have been submitted, and there are so many that I'm going to make this historical introduction very short. Let me start by asking how many of you have seen the movie A Beautiful Mind? Essentially everyone. The movie starts with a slide which is inaccurate. It says Princeton 1947. And John allegedly, according to the movie, came to Princeton in 1947. He didn't. He came in 1948. I came in 1947. And if John had come in 1947, there was no game theory in Princeton at that time. Can everyone hear me all the way to the back?
Yeah.
Good. Literally, there was no game theory in Princeton in 1947. An eminent probabilist, Sam Carlin, who did his PhD in Princeton Mathematics Department in 1947, said he'd never heard the term before he did his PhD and went to the Rand Corporation and was a consultant there in game theory. Although the book, The Theory of Games and Economic Behavior, had been published in 1944, it had fantastic reviews, very favorable reviews, but no research was being done. So how did that change? It came about in the following way. George Dantzig, who was the father of linear programming, was working for the Air Force and had developed this new theory of optimizing linear functions subject to linear inequalities. And he came to Princeton to tell von Neumann about it in the spring of '47. And von Neumann was sort of interested, and he said it kind of reminded him of something he was doing, zero-sum two-person games. And nothing much came of it, but Dantzig came back in the fall of '47, in the spring, rather, of '48, and suggested that there be a university project studying the relationship between linear programming and game theory. And Dantzig had to go back to Washington. He was taken to the train by the associate chairman of the department, Al Tucker, at that time. And Dantzig explained what linear programming was to Tucker. And Tucker thought it was kind of interesting. It reminded him of work he'd done on Kirchhoff's laws. But then Tucker said, I think I'd like to start this project, studying the relationship between linear programming and zero-sum two-person games. And Tucker hired two graduate students, David Gale and myself, in the summer of 1948. This is all before John came to Princeton, to study the relationship between these two subjects. And during that summer, we essentially proved that the mathematics of linear programming and the mathematics of zero-sum two-person games are the same. If you can solve a matrix game, you can solve a linear programming. If you can solve a linear program, you can convert it into a game and solve that. And so in the fall of 1948, when John arrived, we had started a seminar in game theory at Princeton. Now, that was kind of an important event. There were really only 3 or 4 seminars, weekly seminars, that went on either here or at the Institute for Advanced Studies. So it raised the visibility of the subject considerably. And in the period that followed that, Princeton and the RAND Corporation were the 2 locations in the United States where research in game theory went on. Of course, the RAND Corporation was supported by the Air Force, had military applications. We were not. We were just studying the pure mathematics of game theory. And I think in that period we had a remarkable set of accomplishments. I'm only going to put up one slide. This is a quote from Alman's article in the New Palgrave. There you go. I hope that's legible. I'll read it out. The 1950s were a period of excitement in game theory. The discipline had broken out of its cocoon and was testing its wings. Giants walked the earth. At Princeton, John Nash laid the groundwork for the general non-cooperative theory and for cooperative bargaining. Lloyd Shapley defined the value for coalitional games, initiated the theory of stochastic games, co-invented the core with D.B. Gillis, and together with John Milner developed the first game models with a continuum of players. Harold Kuhn worked on behavior strategies and perfect recall, and Al Tucker discovered the prisoner's dilemma. This is a remarkable set of accomplishments for a short period of time, and were really the foundation of the modern theory of games. And I'll let that be an introduction to my old friend and colleague sitting to my right, John Nash, who might tell you a little bit about what he did.
It's certainly true what Harold has described about that seminar being very influential. Professor Tucker, who was organizing, he became a thesis also and had some theses like this. And my talking in game theory became my thesis. And Professor Tucker was an active time. In my early work in game theory, which was while I was at Princeton and graduate student, and I was here 1 year after being a graduate student, I worked on, it led to 6 applications actually that I can mention.
Sorry. I think people might not be hearing you, so let me give you a microphone.
Yes.
Excuse me.
Sometimes these don't work.
Well, this one works.
Am I at the right level? It may be too strong.
Well, I'm going to put it a little bit lower. This better?
Oh, I may be. But I thought maybe it might be good just to name these sort of, because there's one thing, equilibrium points in n-person games. This could be considered as a mathematical result, and it's such a way it's not conflicting with other things. It's like an extension of von Neumann's theory, where he has the minimax, and of course it turns out that that is an equilibrium point. And so if you apply this to zero-sum games, you can infer that. This was submitted late 1949, sent to the Proceedings of the National Academy, which nowadays doesn't have much in mathematics or physics, it's mostly biochemistry. That was sent by Professor Solomon Lefschetz, who was the chairman of the department. And then I referred to von Neumann and Morgenstern in that. Plus also I referred to David Gale, who was a student, he's sort of contemporary of Harold's here. He's in the mathematics department, also important in game theory. And he had reminded me of the Kakutani fixed point theorem, which is a neat version of the sort of the basic truth in the Brouwer fixed point theorem or other related things. But it's been very popular with economists. So soon after I used the Kakutani fixed point theorem in here, there were economists who were using it for general equilibrium. And then I think after this, the bargaining problem may have appeared. And this involved an axiomatic approach to a classical concept of bargaining, but it was set up in mathematical form with mathematical utility, and the bargains available to the bargainers become a convex set of points in a plane where the coordinates are utility functions. And there is a 0 point if the two sides disagree. And it has the axiomatic approach. And I know you've studied that because your questions relate to that. And then you also mentioned the Kallias-Maradinsky solution. And there are alternative solutions. This seemed to appear. So this appeared really before my thesis. Now my thesis was written up, and it's on record in Princeton in the Mudd Library, I think. One copy is missing, and then the next thing is, well, my thesis actually appears, but then it's called Non-Cooperative Games. This is much expanded from this. This was really one page, but it appears on 2 pages in the journal. And this appears in the locally favored mathematical journal called Annals of Math. And then after that, well, there was something independent of that, which I can mention. It turns out that the game of poker is very good for illustrating non-cooperative play. You could have any number, 2, 3, 5, poker players. It's still a quite popular game. We have some television versions of it. And I've seen it being discussed currently in game theory meetings there. People are working on computational studies. So a paper that was, now, Howard mentioned Lloyd Shapley. We were both, Shapley and I, lived in the graduate college as graduate students here. And you in there too, weren't you? You were also in the graduate. I had started looking at a poker game to illustrate the equilibrium point, the equilibrium concept, and I did go into a certain extent on the computing on that. And it turned out you had quite a bit of structure just in a very simplified game to describe all the possibilities. And then that had a model where there were two quantities called the bet and the ante. And that was all there was. You couldn't bet more than once, and you had only a basic ante. But so I calculated first with the size of bet and ante were the same. But then there was a question of what happens if this varies. That was one thing one could vary about the game that wasn't so difficult. And further calculations were done by myself and Lloyd Shapley, who developed, while he was at Princeton, he developed the Shapley value concept. This very nice thing which gives the characteristic function of the game, and then it gives you an evaluation, giving an assigned payoff value to each player. You can argue about the evaluation of whether this or that is the right sort of evaluation, but it's nice to be able to have something, and that is the first one. This was published in an Annals of Mathematics Study volume, and were you editing that? You were editing that series. That was a different area of publication. Then the bargaining problem led also to, with game theory in general, non-problem leads to the possibility, suppose the situation of two persons is not so simple. In the bargaining problem, if they do not agree, then they don't affect one another. There's simply a 0 point. But in a more general situation, they might be able to affect each other apart from agreement. So that led to what I call two-person cooperative games. Well, first, if they do not agree, but they're in a general situation, they might have the possibility to do damage or to do good. So ultimately, I introduced the concept of threats. So this was a game that could be thought of in relation to bargaining in an economic context, and so is this. This is published in Econometrica. This seemed to have quite economic. So this was also published in Econometrica. And later on, this is John Hassani, who was recognized as the economics Nobel Prize at the same time as me, he discovered that an economist a Danish economist working in England named Zuten, I think, had discovered the same concept for a bargaining problem solution. But it was not formulated quite in the same language. Like you could say that the Cournot solution, the French economists back in the 19th century, is the same as the non-cooperative equilibrium. It is, in a technical sense, but he didn't formulate it in the generality of game theory. And so one could say Zuten's solution, which wasn't too much noticed, was not formulated in the general context of game theory. He observed that the product of the profits of two persons in this type of duopoly, a bargaining type of duopolistic situation where maybe they adjust their production rates. If they maximize the product of the profit, that is a good formula. And of course, these questions of what is the right axiomatic solution is still something that can be discussed. There are various arguments that might be given, Frey, Nash, or why Calais, Smorodinsky, or why Rafa, or why maybe some other variant or compoundings. So this was published in Econometrica, and this opened the door for another paper, which I published in collaboration with Martin Shubik was a graduate student in the economics department here at the same time, and John Mayberry was in the mathematics department. And I got together with them, and we applied we applied the theory of two-person, of course I was sponsoring this, two-person cooperative games to a duopoly problem. That's where there are two producers, they're producing essentially the same thing, like two dairies producing milk in the area of the same town. A comparison of treatments this is Mayberry Nash Shubik. Martin Shubik became an economics professor at Yale. Of course, these people are all pretty old now, like me. This was in Econometrica. Well, now, this business about the Nobel Prize, I think there's a sort of an angle here. If these papers had not been published in Econometrica, I would have been under consideration. And the mathematics were really separable. But there were three things published in Econometrica. And then there's one other early publication, yes, where this was simple three-person poker game. This was published in that special, yes. Well, now there have been some books that have some of these. One of them is Princeton University Press. This is called The Essential John Nash. I don't quite like the title of this. And this has some collected publications of mine, things where I've done work as well as other things. It has the part of the thesis that's in the library of the university that was not in the published paper. The published paper was written in more of a mathematical style, annals of math, and this discussion about mass action and collective behavior, that was sort of dropped out of it. But this book has that. And there's also another book, the publisher called Edward Ellery Company. They approached me soon after I became better known, and they would do sort of a book collecting my publications on game theory, not everything. See, this has things that are not in game theory, but there is also something called Essays on Game Theory. This has everything of the game theory type. It has the poker game, it has everything, it has the thesis. This is Edward Elgar. But now, after the time that I was a graduate student at Princeton, I went on and I became an instructor at MIT, and then I moved up through the ranks there. For a certain number of years I was there, and I got into various things. Ultimately, I was in partial differential equations. But before that, I was in differential geometry to some extent, and I got a major result, a classical problem, the embedding of a Riemannian manifold in Euclidean space so that the metric was induced by the metric of the space. This has a vague analogy with string theory somehow, then that you need at least 10 dimensions in order to induce a metric on a manifold of 4 dimensions. That's even in the local form, but as far as the results I was getting to a closed manifold of 4 dimensions, I was requiring much more than 10 dimensions. I think he came out for 46. I was working with positive metrics, but it naturally would extend to indefinite metrics like in general relativity. And then before that, I did something, I completed work on an idea that I had as a graduate student in Princeton. This became a paper called Real Algebraic Manifolds. And that was also published in the Annals of Mathematics. And that was what I was thinking could have been my thesis if the thesis in game theory was not accepted, but the thesis in game theory was accepted. And I finished writing that up at MIT, and that was published. It was called, sometimes it used to be called Nash manifolds sometimes. And the work has been continued by, notably by an Italian mathematician.
Thank you very much. As I had said earlier, we'll have a question answer now. And I went over all the questions with with other activists, and they thought the sheer number and variety of the questions were already a sign of how interested and the class learned how interested you are in game theory. They picked out some as questions that they definitely want to see, want to do first, and we'll try to do as many as we can in this time. But so Sam and I are going to try to go around. Some of you ask many, many questions. So whenever you get the microphone, please ask one of them, and then give a chance to somebody else. So the very first question, I'd like, I don't see him right now, Vishal Shalani. Oh, here. So, in case you've forgotten your question, I actually brought a printout. So, you can see it from the printout.
So my question's for Professor Kuhn. Among other things, you're really well known for Kuhn poker. It's a sort of two-person simplification of poker. And I've played poker a lot, and particularly I've played heads up, which is like a one-on-one player form of poker. And I was wondering if you think that the extension of the analysis to a game with more complicated hands rather than just a high card winning thing is feasible for poker. And if indeed, would it actually be useful in the real world? For instance, I know that in the results of Kuhn poker, some of the optimal strategies are mixed strategies. And it's a discussion that I've had a lot with other people as to whether or not human beings can actually play mixed strategies randomly, as they would have to be played, right? And if not, could we design a computer to do that? That could beat human beings that use tells and other psychological, non-mathematical things?
Okay, that was a long question.
I'm delighted to answer.
Longer than written.
I'm delighted to answer this question. It's very timely. There was in the New Yorker magazine 2 or 3 weeks ago an article written by Alex Wilkinson, and I think the title is "What Would Jesus Play?" And the reason it's called "What Would Jesus Play?" because it's describing a PhD in mathematics who's also a champion in the Las Vegas World Championship of Poker. His name is Ferguson. He has a PhD in mathematics from UCLA, and his father is a professor of mathematics at UCLA, and they've both written on game theory applied to real poker. And I recommend this article very seriously to you, because Ferguson does apply game theory explicitly to his play, does do randomization. Now, the question of randomization in poker is a curious one, because von Neumann Morgenstern introduced mixed strategies, which are probability distributions over pure strategies. Roughly speaking, a pure strategy is a book which gives you exactly what to do in every situation when you're called upon to act, and then you derive a probability distribution of these books. But in poker, you're at a certain situation, at a certain information set, and players generally randomize on the occasion of a choice rather than randomizing over the pure strategies. And you either bluff with a certain probability, or you see or call or whatever on the occasion of the action. Behavior strategies, which I studied in the early 50s, work in games of perfect recall, of which poker is one. And so players intuitively reduce the dimension of their actions enormously by this. And you can read in the article how Jesus, Ferguson, he's known as Jesus, he looks a little bit like Jesus. And the picture randomizes on the occasion of a choice. I think since we have a long list of questions, I'm going to let that answer suffice. I'm quoting the article with the one thing I know is true. Very simple models, like the one that John mentioned, or the one that I did of two-person poker, show you that bluffing is absolutely necessary to get the optimal result. And that was an exciting result, to find that this psychological phenomenon really took place in a mathematical model. Okay?
Okay, so let's go to the next next question, do you see? Oh, there. Okay. So maybe let's, while the microphone travels to Mark, let's have Kate's question. Kate Ferguson.
My question is there any current research on an application of game theory that you find particularly interesting or unusual? If not, what do you think is one of the more interesting or unusual applications studied in the past?
I think that's one which we would like both your answers. So the question was, Kate's question was,
do you think there's some applications that are particularly interesting, or what did you find the most interesting one you've seen in the past of game theory?
Well, that's a little difficult for me. I don't know everything that like is being done, and I might guess something.
Okay.
I found some needs.
But most interesting that you have seen, or do you want not to show any preference for all these children?
It's interesting, for example, that you can reduce a traffic problem in game theory sometimes.
Oh, I hadn't thought of that.
Optimizing traffic flow.
We'll have to find a homework problem on that.
Well, professors ran out of help in that, and also, of course, there are experimental games. He's interested in that.
Okay. Yes?
For about a period of 23 years, I was a principal in a consulting firm which was located in Princeton called Mathematical, not related to Wolfram's Mathematica in any way, shape, or form. And we did a number of applications of game theory, and I would mention just one, which has always been close to my heart. We did the first theoretical contract for the Arms Control and Disarmament Agency, in which we formulated inspection games. At that time, the United States and the Soviet Union were engaged in negotiations over the possibility of allowing inspections on Soviet soil. The possibility of a nuclear experiment by Russia would be confused by seismic activity in the Soviet Union, and the strong possibility that they would try to hide experiments by performing them in areas where there was seismic activity. And the question was how many inspections a year would be sufficient in order to guarantee a certain level of satisfaction that we had discovered any experiments that they performed. And when we formulated this game, we suddenly realized that you don't want to negotiate the number of inspections per year because you might use them up. You should have a continuing overlapping system. And we recommended that to the negotiators, and they took it to the negotiating table, but unfortunately no treaty was ever negotiated. But it was a lovely bit of game theory. It's reproduced in a book by Sati on mathematics of arms control, and they're called inspection games.
First, thanks for coming out. My question is to you, Professor Nash. You came of age in an era where large reliance on computing was not a major part of most academic research. Do you think in modern day that using computers to analyze and solve problems is a big advantage specifically to the field of game theory for large and complex games with many players where computations by hand are not really feasible? Or do you think theories and principles are really all that's needed?
I think the computing is very relevant in some of the contemporary challenge. I've been working in the last so many years, sort of a later career phase, on something that specifically involves that. It's just three-person games, but it's the type of three-person property game where you could apply the Shapley value, or you could apply an alternative thing called the nucleolus. Maybe other things can be applied to games like that. And it's an attempt also to model the cooperation in terms of a non-cooperative process, regarding the idea of the evolution of cooperation, which can occur in nature. And my approach to modeling brings in computation, because one wants to find a certain type of equilibrium described by a large number of parameters, even though there are only 3 players and very simple action. But the computation is heavy, and there's various computational challenges that are coming up. I think that it's really the future, but you have things become possible now that were not possible earlier. We have the 4-color conjectures considered as solved, but that was done with computers. There's still arguments about it and how it should be done, but it seems that we wouldn't be there at all without computers. The weather is gradually the weather forecast improved, and that's a matter quite ready to use. And game theory is not entirely distant from weather meteorology or financial analysis. You would like to know what the stock market will do the rest of the day, maybe, or tomorrow. That's sort of analogous to a weather prediction, but it's not easy to get that type of weather prediction.
Let's go to the next question.
Hi, thank you so much for coming. I was just a question about Professor Nash. Who was your inspiration when you came to grad school to start studying game theory? Since as y'all said, it's a relatively new subject of practice at Princeton.
It's hard for me to remember the details, but I certainly was influenced by the seminar that apparently had only been started the summer before I came. And Professor Tucker, who became my thesis advisor, was the organizer of that. And behind that, there was Nancy and Ryan. And also, I think the fact that Morgenstern and Van Neumann, the authors of this book, were in the area. This must have been a big influence.
If I might add a tiny personal detail. Over lunch, I was talking to Ingrid, and I realized that I taught the first course in game theory at Princeton. In fact, possibly their first course in any university in game theory, and it was 2 years before she was born.
So you see,
I won't be on general.
Our next question is from Mohit Agarwal.
Thanks for coming. I had a question about the future direction of game theory. So if you look at the board, Professor Nash was lecturing, these articles are all from the early 50s, 1950s. Where is game theory headed today? And are there major theoretical problems that they solve, or are there only good applications yet to figure out?
You were asking this, I should say. I think it's really difficult to say in a very wise and prophetic manner where any sort of theory or any sort of thing that's called a theory is headed. You could have the promoters who would be saying one thing, detractors might be saying something else. So you could say, well, where is psychoanalytic theory heading? There are probably more people that disbelieve in any validity of psychoanalytic theory nowadays than there are that believe it has validity. Is there is heading very difficult?
If I might add a comment or two. There is an international game theory society which held its first international meeting, I think, in 2001 in Bilbao. And I went through the exercise of looking at the members, the charter members of the society, and only about 5% of them are mathematicians. The rest are economists, sociologists, statisticians, computer scientists, applied people in short. And I think the transition from a period in which we were doing pure theory, which I alluded to as excerpt from Alman's article, is somewhat past, and that there are not outstanding theoretical problems of any great interest. I think the interests currently are, by and large, to applications. This volume that I have here is the 60th anniversary edition of von Hardt and Morgenstern, and there's an afterword by Ariel Rubinstein, a distinguished Israeli game theorist in that volume. And he says something like, the well of game theory has run dry, which is very pessimistic. In fact, we had to send this back to him to rewrite it. It was so pessimistic about the future. You don't want to publish a new book on game theory and say the well of game theory has run dry at the same time. But he had a point there that the outstanding problems are more in the areas of applications and interesting applications. We see a very vigorous development in behavioral game theory right now. The Nobel Prize for Kahneman was evidence of that. Taking into account irrational behavior and psychological aspects which the mathematical theory of the classical sort did not. I sometimes love Hardt and Kolbe. I'm rather with Ariel Rubinstein that theoretical mathematical problems are not there right now. There are very few that have been posed and not solved. On the other hand, there was a presidential address by Bob Alman at the meeting in Bilbao in which he listed a set of theoretical problems which he considers interesting. One of the questions that was in the list that Ingrid gave us earlier today dealt with the question of games with incomplete information where you don't know what the rules of the game are, you don't know how many strategies you are, you don't know the evaluations of your opponents. And some progress has been made on that by Alman and Moschler, but there's lots of interesting questions there. I don't know whether that's a satisfactory answer, but neither of us is a seer of the future in that regard.
And I'd like to add 100% to that. I mean, history is replete with people being quoted as some field is dead, we've done everything. I mean, physics has been all done a matter of years before quantum mechanics was discovered. I mean, so I think statements like "this is over, we know it all" should never be taken certainly not for gospel. I mean, the interesting ideas are always the ones that come out of complete left field, and you didn't see them. I mean, that's why they're so interesting, and they can lead to completely new developments. But I shouldn't go on. I mean, next question, please. Oh. But we have lost the microphone. Sorry.
This question for Professor Nash. I read that you started off your undergraduate career leaning towards chemistry or chemical engineering. And I was wondering if there was a particular event, particular person, or class or field in math that really got you interested in math.
Well, I went to college at Carnegie Tech that was in Pittsburgh, and I happened to have a scholarship to go there, which was well, maybe 90% of the undergraduates and part of the music degree, and it was a Westinghouse scholarship. Pittsburgh is where Westinghouse Corporation at that time had their main center. I went there, my father was an engineer, electrical. At one time I thought that I could be an electrical engineer, but then I had interest in chemistry and mathematics also, and general interest in science. And it seemed practical to study chemical engineering. I think Von Neumann here, who's one of the authors of this theory, he became a mathematician, but he first studied chemical engineering. He started out in Hungary. So it's a field that is seen, it's still a good field for people going into it because the starting salaries are very good for chemical engineers. And when I reached Carnegie, I found that some of the requirements for the engineering curriculum, particularly those involved drafting and working carefully to make a detailed blueprint like drawing, were not quite to my taste. I had an irregular style of handwriting. It was a little difficult, and I found also that the scientific, you could be a scientist and not good process. I was persuaded to shift into chemistry. And then there were some very influential mathematicians there. There was Professor Duffin, there was Professor Rosenbach, and Moskowitz. And then John Light Singh was briefly there, and he went on to other places, ultimately to Dublin. And those people influenced me to pursue the career in mathematics. So that it wasn't a practical thing also. So by the time I reached the junior level, I guess, I was operating on a trimester basis. I was operating on a 3-year basis after the war with summers. We were studying full summers. So I shifted into mathematics later on. And then from there I came to Princeton with a little stopover in the summer, something called the Naval Ordnance Laboratory, which is outside Washington. That gave me a little exposure to fluid mechanics.
If I might add a footnote that I'm sure John would not tell. He's mentioned his advisor, Duffin, at Carnegie Tech, who was a very good friend of Al Tucker's. And Duffin wrote John a letter of recommendation that you would kill to have for yourself. He wrote a single line saying, "This man is a genius."
That's quite a recommendation letter. I have never seen one like that myself. I have never written one like that myself. Is Robert Button here? I mean, we don't see. Oh, there you are. Okay. So our next question will be from Jessica Zook, but the question after that will be yours.
This is a question for both of you. Are you working on developing any theories today? If so, like any sort of research or studies, even if it's just in your free time, if you could tell us a little bit about what you're currently looking at.
Well, I mentioned before, I have been working on something that leads to computations. It's a model of the 3-person cooperative games. One could consider specific examples where the example is defined by characteristic function. Although I worked in my game model didn't quite get the characteristic function concept, but it didn't quite get transferred from the theory to the technical point. But that definitely involves games, and it also involves the modern possibilities of computation. And a publication about that is in process, but much more could be done. I might be able to get support for further work. I had a NSF project support for a time, and some Princeton students worked as project assistants. First there was someone in mathematics, then there was someone in economics, then another person in mathematics.
I'm not working in game theory right now at all, but I've been re-examining a favorite child of mine, which is called the Hungarian method for the assignment problem, which is an algorithm I devised 56 years ago, something like that. It was the first polynomial algorithm for any large class of linear programs for the transportation problem and the assignment problem. And we had a 50th birthday party in Budapest 4 years ago. And so I had to re-examine it, and I was looking at the geometric interpretation of the Hungarian method, which had been proved by a German professor, Schmidt, to be a greatest descent method in a certain space. And I suddenly realized his choice of space and his choice of variables were very odd. And if you made different choices of space and variables, you could get very different performance for the algorithm, and you get increments which are not Edgevari or Koenig increments. And so I've been exploring this in recent years, trying to get something new. I tell you, at our age, it's quite a rush to get anything new at all.
Next question.
My question for Professor Kuhn. What came first, your interest in nonlinear optimization or your interest in game theory? And since the two fields were still in their development 50 to 60 years ago, how, if at all, did the two fields complement each other?
If I go back to 1948 and 49, Gale and Tucker and I did this basic work on duality of linear programming, and Tucker went off on leave to Stanford. Indeed, he was on leave while he was directing John's thesis. And he proposed to both David Gale and I that we do a paper on quadratic programming rather than linear programming. And David Gale had had enough of programming and optimization. And I responded saying, let's not do quadratic programming, let's do general nonlinear programming. And so we composed this paper between Princeton and Stanford during the spring of 1949. I was simultaneously working on my thesis, which was not in game theory or optimization, but rather was in algebra and topology under Ralph Fox, eminent authority on knot theory. Meanwhile, Tucker and I were editing the first volume of the Contribution to the Theory of Games. So I guess it was a case of multitasking. I'm not sure that I know which influenced the other. Optimization has been an interest all my life, but largely for combinatorial problems. Nonlinear optimization is an extremely practical subject and has gone far beyond the results of the Kuhn-Tucker paper of 1949-50. And I haven't done very much in that. I'm more interested in specific algorithms like the Hungarian algorithm. Thanks.
And I can tell you that that's a field that's very, very alive. In fact, I have been in the last few years working very much on trying to understand algorithms and get some better ones for huge matrices. And we're still in the business of finding it. Next question is for Peter Goodmanson.
As a lacrosse player, I find that game theory appears sometimes in my everyday life. For example, during practice, if I dodge a certain way and my defender uses a certain type of move, my move has a certain probability of working. I was just wondering, if this is for both of you as well, if you find any real-life applications to game theory in your life, and if so, how do you combat that?
I know that game theory has been connected with the games on the field, with ball and sort of this, particularly there's been some discussion of the, I think in the soccer or generally in the world football game, that you have this goal area, this sort of frame and the goal, and there's a goalie there who is defending. Now, but you can have attack and defense is a natural game situation. The question could be, suppose you could you can aim the shot 3 ways towards the goal area, left, center, or right. How should that be done from the game point of view? When the idea, what you want is that the goalie is going to fail to get it and get through. This has been considered game theory. I can't remember exactly what the conclusion was, but it's something where you can have a mixed strategy. And the idea is the goalie, if he's on one side, you can't get to the other side for the puck gets there.
We are nearing the end of...
Recent. I mean, I've heard conversations about this recently. This football.
Have any game coaches ever approached you about about strategies and things like that?
A game coach?
Yes.
I've never been very good as a game player. I think sort of 0.
No, but they might have asked you about you're not maybe an expert player, but an expert strategist.
No, I don't think so. I heard sort of kind of this is a second hand. This is a more abstract level.
We're near the end, but we have a question from Mohit Agrawal again. So.
All right, so I have a 2-part question. These questions are for both of you. One would be, since you are a professor at Princeton and you happen to be the 4 founders of this field, which fundamental courses would you take as an undergraduate today? I know Professor Nash talked about chemical engineering. I know Princeton talked about the liberal education, they should take classes and all of that. But if you were to be an undergraduate today, not just game theory, but in general, if you were an undergraduate, what would be the 2, 3, 4 main core courses you would really like to take? And then the second part is, if you had one sentence for us to take away about game theory, what would it be?
Some of our advice about courses, and then what would you like students to take away?
It's easy to talk about courses, but I think I read that question. There was something about persons interested in economics and mathematics.
Yes.
Because it makes a difference if you're interested in some sort of languages or cultural study, then you could be far enough away that you would want to choose different courses. Well, what I've observed about economics and economists is that it seems to help them to have mathematics and breadth. Because being an mathematician, I start from that point of view. Of course, one could always have more. Mathematics can't know it all. But mathematics mathematics generally seems to be good for people who are concerned with economics. Nowadays, there's been a crisis on Wall Street, the banks globally, and at the same time there are these hedge funds, and there's one mathematician operates a hedge fund, but he seems to be able to sail through the crisis times quite well if his bets well hedged. But there's a category of people that we call quants, and you only need a bachelor's degree in mathematics to go to Wall Street and become a quant. Of course, you might not be hired at some places, you might be hired. But the quants seem not to have been the people who were fired recently when all the troubles have come up. They seem to have been holding their positions mostly. So that suggests that the mathematics background is good.
I think I'd answer, take as much mathematics as you can. It's all beautiful. And I take combinatorics, take graph theory, take complex analysis, one of the more beautiful subjects in the world, take real analysis, take everything you can. I had a joint chair at Princeton for 38 years in economics and mathematics. And if an undergraduate came to me and asked, should I major in mathematics or economics? I want to do graduate study in economics. I'd say major in mathematics and take as much as you can, then go off and do your economics. The mathematics will be useful. If it isn't, it's beautiful. You'll enjoy it. And, take everything from symbolic logic to graph theory. As for a takeaway, you're looking at two very lucky men who were in the right place at the right time. I think game theory has clearly entered the heart of economics, no doubt about it. You can't do theoretical economics without game theory. As for other applications, I think that remains for the future. But we were lucky to be in at the beginning.
Okay, and on that note, we'll end. It's also almost the time of the end of our class. So let's thank our speakers again.